TechDaily.ai, your source for technical information. This podcast is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup, disaster recovery, hyper-converged in VMware, Hyper-V, Proxmox cluster, AI servers, SA365, a turnkey security appliance in public and private cloud. Check out stonefly.com or email your project requirements to sales@stonefly.com. Okay, let's dive in. Imagine holding a single hard drive.
Yeah.
The same size as they are now, maybe in your PC, maybe in a server somewhere.
Standard form factor.
Exactly. But instead of like a few terabytes, maybe 10, maybe 20, this one holds 100 terabytes.
Wow. Yeah, that definitely sounds like science fiction, something way off in the future.
Right. But what's really fascinating and why we're talking about it is that this isn't some, far-off dream anymore. It's actually becoming, well, a very real near-term possibility thanks to some pretty serious tech advancements.
Exactly. So yeah, for this deep dive, we should really unpack what's happening here. It seems potentially revolutionary in the world of data storage.
For sure.
We're looking at efforts, particularly from, a big player like Seagate. They're making a huge push with this technology called HAMR, heat-assisted magnetic recording.
Okay.
And they've built this new platform around it called Mosaic. So our mission, I guess, is to figure out what HMR and Mosaic actually are.
Right. And why now? Why is it suddenly so critical?
Yeah, why the urgency, and what does achieving these kinds of capacities like that 100 terabytes you mentioned, what does that really mean?
Because, yeah, it's not just, butter drives. It feels like it could enable, I don't know, the next big waves of tech, right?
Yeah.
Handling this absolute flood of data that's, well, it's already here and it's only getting bigger.
It absolutely is. And if you look at the big picture, the demand for data is just exploding. I mean, frankly, everywhere, every industry. And the ways we've traditionally built storage, they can't keep pace much longer. We've kind of hit fundamental physical limits with the existing tech.
Right. Like squeezing blood from a stone at this point.
Sort of, yeah. So finding fundamentally new ways to cram significantly more data into the same physical footprint, it's absolutely crucial for the future.
And that brings us right back to Mosaic, doesn't it? So this Mosaic platform, that's Seagate's path, their roadmap to hit that potentially game-changing 100 terabyte capacity.
That seems to be the plan, yes.
How do they actually get there? What's the key technical step?
It really centers on dramatically increasing the storage density on the actual spinning disks inside the drive, the platters.
Okay.
The big milestone they're aiming for is packing an incredible 10 terabytes onto one single platter.
10 terabytes on one platter.
Yeah. And they've made, significant progress already. Right now, they're actually shipping drives with 3 terabytes per platter.
Okay, so they're already partway there.
Exactly. But their roadmap, what they're showing, indicates a clear path, and they seem pretty confident they can scale that density up to the 10 terabyte per platter goal.
Okay, hold on. Just so I can wrap my head around that scale. 10 terabytes on one of those thin, shiny disks inside a standard hard drive, that's already amazing density.
It really is. And, well, here's where the math gets pretty exciting. If you can hit that density, the 10 terabytes per platter, and then you combine that with a drive design that uses, say, 10 platters stacked inside that standard 3.5-inch box.
10 times 10.
That's exactly how you get to the potential for 100 terabytes in one physical drive.
Wow, okay. Which raises the big question, though. Why do we suddenly need that much capacity, like right now? What's driving this huge jump?
And that's where the AI connection gets really, really interesting. It's not the only factor, but AI is definitely a massive accelerator here.
Right.
This capacity jump is directly tied to that exponential data growth we talked about, especially though not exclusively from AI and machine learning.
So what is it about AI workloads specifically? What demands are they putting on storage that pushes us towards needing 100 TB drives?
Well, AI and machine learning training, it's just incredibly data hungry. And not just the initial data set size either.
Right.
For instance, they need much more frequent checkpointing during the training runs.
Checkpointing, like saving your work in a game.
Kind of, yeah. Think of it like creating save points. AI models are so complex and training takes so long, days, weeks sometimes, that you have to constantly save the model's state, its progress, all its learned parameters.
Sure way.
Because if training gets interrupted for any reason, you can just pick up from the last checkpoint instead of starting the whole thing over from scratch.
Okay. That makes sense. But saving that whole state must generate a lot of data.
Oh, enormous amounts. Saving the entire state, maybe every few minutes, maybe every hour during a process that runs for weeks. It generates absolutely massive volumes of data very, very quickly.
Right, so saving your work, but your work is this gigantic multi-billion parameter thing.
Mm-hmm.
Okay, what else?
They also need higher fidelity data. AI models just perform better when they're trained on richer, more detailed data sets.
Like higher resolution images.
Exactly. Higher res images, more complex simulation outputs, vast libraries of really high quality text or audio. Just feeding these models means storing these huge, detailed data sets to begin with.
Okay.
And maybe most significantly, they require much, much longer data retention windows.
Keeping the data around for long.
Way longer. Once an AI model is trained, you often need to keep everything. The original training data, every version of the model itself as it evolved, all the intermediate results, the logs, potentially for years, maybe even indefinitely for regulatory reasons, or just to validate the model later on.
So it's not just the data you use today, it's keeping this whole historical trail.
Precisely. It's the long tail of data retention that really adds up.
So it's generating more, it's higher quality,
Yeah.
and you have to keep it basically forever.
Okay. And while AI is obviously huge, you said it's not the only driver pushing storage limits.
Absolutely not. There are other big factors fueling this data explosion. Think about richer content creation everywhere.
Like YouTube videos getting higher resolution. Yeah, individuals sharing 4K, 8K video, businesses generating incredibly detailed sensor data from, Internet of Things devices, complex 3D models, simulations. The size of just individual files is ballooning.
Right.
Then there's all the data transformation and replication happening inside big systems. Data gets copied, processed, moved between different storage tiers, backed up, replicated geographically for disaster recovery.
All those copies add up.
They really do. It multiplies the storage footprint significantly.
And you mentioned retention before, even outside of AI.
Yes, extended data retention policies are just becoming the norm in so many industries now. Financial records, medical data, communication logs, regulations, and basic compliance often mean you have to keep data for years, sometimes decades. No choice.
Which leads to another huge factor you touched on. Regulatory stuff,
Right.
especially data sovereignty.
Oh, absolutely. This is massive. We're seeing rules popping up in country after country dictating where data has to physically live and for how long you have to keep it there.
How many are we talking?
The number cited is over 150 country-specific data sovereignty regulations now.
Wow, 150.
Yeah, and if you're a global business trying to comply with all of that, it often means you have to make multiple copies of the same data and store them in different physical locations, potentially under different retention rules for each location.
That sounds like a nightmare, just pure complexity and duplication.
It is. It's a huge driver of storage consumption. That complexity, that duplication, it really forces companies to buy more storage.
So, wow. It sounds like retention, just keeping data around, isn't just a small piece of this. It's actually becoming as big a driver, maybe even bigger sometimes, than generating the data in the first place.
Precisely. That's a really key point. And this whole situation is where the economics become absolutely critical.
Right, because storing all that data costs money.
A lot of money. And the traditional way of making hard drives using what's called perpendicular magnetic recording, or PMR.
That's the standard tech we've had for years.
Yeah, the workhorse. It's really hitting a technological wall now. They've kind of reached a plateau in how much data they can reliably squeeze onto a single platter, and also how many platters they can physically cram into a standard drive enclosure.
So they've kind of run out of easy ways to make drives bigger using PMR.
Pretty much, yeah. The easy gains, the low-hanging fruit in terms of capacity increases, seem to be largely gone for PMR in the last few years.
Okay, so the familiar tech is stalling out. How does this new HAMR technology compare? What's its potential for density?
Well, HMR, heat-assisted magnetic recording, it's fundamentally different. And crucially, it hasn't hit that same wall. Not yet, anyway. While PMR density growth has slowed way down, HMR's potential seems to be continuing to advance pretty significantly. If you look at the trend, PMR drives got bigger mainly by adding more platters, but the density per platter slowed.
Right.
HMR, on the other hand, shows this clear path to really substantial increases in the density on the platter itself. And that directly translates to overall drive capacity without needing, weirdly large drives.
So that's why Seagate is betting big on it. They see it as the way forward.
It seems so. They're arguing that AMR-based Mosaic drives offer the viable solution for the future, especially for those really massive scale deployments. Think hyperscale cloud data centers, huge enterprise archives, places where cost per gigabyte and just sheer scalability are absolutely the top priorities.
And the economics, you mentioned they're stark. Can you give us those cost comparisons again that really drive home why HDDs are still relevant?
Yeah, they really do. So hard disk drives right now for bulk storage, you're looking at prices below 0.014 per gigabyte. So less than 1.5 cents per gigabyte.
Okay, incredibly cheap per unit of storage.
Exactly. Now compare that to NAND flash memory, like in SSDs. For bulk SSDs, you're typically looking around $0 to tens per gigabyte.
Okay, so roughly 6 or 7 times more expensive than HDD.
At least. And then you look at DRAM, system memory, that's exceeding $3 per gigabyte.
Well, okay, that's like 200 times more expensive than the hard drive storage.
Yeah, the orders of magnitude are huge. So even with all the hype about flash getting cheaper, and it is getting cheaper, hard drives remain dramatically more cost-effective for storing truly vast amounts of data at scale. It's just simple economics.
Which explains why they're still the backbone for like Google Drive or AWS S3 or Azure Blob Storage, right? All that cloud stuff.
Absolutely. That and large edge deployments where you need big capacity locally, but maybe not top-tier speed for everything. For those scenarios, massive capacity, lowest possible cost per gigabyte hard drives are still the undisputed king.
Got it. Makes sense.
Although it's worth mentioning, the flash industry isn't just sitting still. They are also working on ways to lower costs for higher capacity flash, even if it means maybe lower performance than your typical high-speed SSD.
Like those C2 standard SSDs, is that an example?
Yeah, things like that are emerging. They're trying to find niches where flash can compete better on cost for certain bulk data tasks, but still they're significantly more expensive per gigabyte than HDDs today.
So for the sheer exabytes and beyond, HDDs with tech like HAMR look set to maintain that cost advantage for a while.
That seems to be the bet, yes. Extending that lead in density and therefore cost effectiveness at scale.
Okay, that covers the why and the economics pretty well. But let's pull back the curtain a bit on the how. How does HAMR actually work? Heat assisted. Sounds like you're cooking the drive or something.
Yeah, it does sound a bit exotic. And it is technically very complex, which makes sense when you hear it's been in development for, over 20 years?
20 years, wow.
And represents a huge investment. Over $1 billion in R&D reportedly went into getting HAMR to this point.
Okay, so serious commitment. What's the core idea then? Simplified.
The core concept, yeah, when you boil it down, is actually quite clever. HAMR uses a tiny integrated laser right there in the read-write head of the hard drive.
Wait, they put a laser inside the head? That tiny thing that flies over the spinning disk?
Yes, precisely. It's incredibly sophisticated engineering. And this tiny laser is used to temporarily heat a microscopic spot on the magnetic recording media, the platter surface, right before the data is written to that spot.
Okay, temporarily. How hot and how fast are we talking?
Very temporarily. We're talking heating it extremely quickly, like within nanoseconds, and to a very high temperature, around 800 degrees Fahrenheit or 450 Celsius.
Nanoseconds, okay. And why? Why this sudden blast of heat?
It's because the magnetic materials they need to use to achieve these much higher storage densities, to pack the magnetic bits closer together, these materials are inherently more magnetically stable at normal room temperature.
Which sounds like a good thing for keeping data safe, right?
It is. It's great for stopping the data degrading over time once it's written. That's crucial for long-term storage. But that same stability makes it much harder to actually write the data in the first place using conventional magnetic fields from the right head. They're just not strong enough to flip the magnetic state reliably on such stable material.
So the stability works against you when you try to write.
Exactly. So by momentarily heating that tiny spot with the laser, they temporarily reduce the magnetic stability of just that little area. Makes it significantly easier for the magnetic write head to flip the bit to write the data to that specific spot.
So the heat is like a temporary lubricant, almost.
No.
Making the material receptive to the magnetic signal just for an instant.
That's a good way to think about it, yeah. And then as soon as that spot cools down, which it does almost instantly because the heat source moves on and the surrounding platter acts like a heat sink.
The data bit is locked in, stable again at room temperature.
Exactly. Locked into that tiny spot very stably. And because this temporary heating allows them to write much smaller, more tightly packed bits than they ever could with PMR.
Tighter bits means higher density.
Higher areal density, yes.
Right.
Literally more bits of data packed into every square inch of the platter surface. And that directly translates to significantly greater storage capacity on the same physical disk size.
Got it. So KMR is like trying to write on a surface that's a bit too hard, making your marks big. HAM is like momentarily softening just the tiny spot you want to write on, making a smaller, precise mark, and then it hardens right back up.
That's a pretty good analogy, yeah.
Okay. So after 2 decades and $1 billion,
Yeah.
is this tech finally ready? Is it really happening now?
Well, that's certainly what Seagate is confidently asserting. They're framing HAMR not as some lab experiment anymore or a niche thing.
Right.
They're stating it's a mature manufacturable technology, and they're implementing it in their latest generation of high-capacity drives, the ones they call Mosaic 3 plus SARD.
Mosaic 3 plus 5. Okay.
And crucially, they say they're moving these Mosaic 3 plus drives, the ones using HAMR, into volume production.
Volume production, that's always the key phrase in tech, isn't it? It means they're serious about scaling it up for real customers.
It really is. It signals they believe the tech is robust enough for mass manufacturing and, large-scale deployment. Not just hundreds or thousands, but potentially millions of drives aimed at those big enterprise and hyperscale customers.
That makes sense.
Though, it's always important to add the caveat. The details show that performance and reliability in real-world production workloads over the long haul are still going to be the key evaluation points for those big customers.
Oh, for sure. Enterprises and hyperscalers won't just swap out millions of drives without kicking the tires hard.
Exactly. They need rigorous testing. They need to see how these drives truly perform and, critically, how they hold up under heavy, continuous use for years and years in a demanding data center environment. That's always the real test for any new storage tech.
Absolutely. Performance under pressure, day in, day out. That's everything. But assuming it does prove reliable at scale, what's Seagate's bigger picture here?
Yeah.
Their strategic vision with this whole HMR and Mosaic push.
Their vision seems incredibly clear, actually. Based on how they've presented it, they really intend to use HMR and the Mosaic platform to, lead the industry in high-capacity storage.
Take the lead on density.
Yeah. Their explicit goal is scaling towards those massive capacities, 100 TB and potentially beyond. And by doing that, they aim to directly solve those really pressing storage pain points we talked about earlier.
The ones driven by AI, analytics, all that regulatory stuff.
Exactly. The pain points introduced and really amplified by this exponential data growth, particularly from AI, but also analytics, and that increasingly complex web of global regulations driving those long-term retention needs.
So it's a very strategic bet. They're positioning HMR and Mosaic as like the necessary foundation to handle the data demands for the next decade.
Right.
Especially with AI booming and regulations getting tighter.
That's exactly how it lists. The implication is pretty clear. If adoption meets their hopes, this technology could fundamentally shift the economics of mass storage for the foreseeable future.
Making it actually feasible, economically and physically, to store way more data for much longer at a scale that maybe seemed impractical or just way too expensive before.
Precisely. It could really change the game for how massive amounts of data are handled.
That's potentially a huge impact across pretty much every industry, isn't it?
It truly is.
Okay, let's maybe try and synthesize this a bit. We started with this almost sci-fi idea of a 100-terabyte hard drive.
Right.
And we saw how technologies like AMR and Seagate's Mosaic platform built around it are working to make that real.
Mm-hmm.
Based on hitting that incredible 10 terabytes per platter density goal.
Mm-hmm.
We've seen the urgent need for this isn't abstract. It's being driven right now by AI's, frankly, insatiable hunger for data needing constant checkpointing, higher fidelity data sets, massive long-term retention.
Yeah, all those factors combined.
Plus just general global data growth from everything else and that crazy complex web of data sovereignty rules forcing longer, more spread out storage.
Right. The retention and compliance piece is huge.
And we looked at the economics. The clear reason why hard drives are still so critical at this scale, remaining dramatically cheaper per gigabyte than flash for just storing bulk data.
That cost difference is key.
And finally, we touched on the cool tech making HAMR possible, that tiny laser doing precisely controlled, temporary heating, to allow much tighter bit placement on the platter.
Yeah, the physics and engineering behind it are pretty amazing. It's a fascinating convergence of needs, economics, and innovation trying to break through those old limits.
So, for you listening, maybe take a second to consider the implications of this kind of leap. Think about the sheer volume of data that trains the big AI models you hear about.
Or the requirements for companies to store vast archives for compliance, not just for one country, but potentially dozens, maybe hundreds for years or decades.
Or just the sheer scale of the infrastructure needed for the cloud services we all use every day. Storing data for billions of people, petabytes of corporate info. How does a single drive holding maybe 100 terabytes change that whole picture?
It fundamentally alters the calculations, right? Space in the data center, power consumption, cooling needed, and obviously the cost per terabyte stored.
Which leads to a really interesting thought for the future, I think. If, say, 100 terabytes per drive does become commonplace, making storing, well, practically everything, or at least way, way more than we do now, feasible from a cost and space perspective.
hmm
What does that unlock?
Yeah, what new possibilities open up? What kind of data analysis or huge simulations or long-term digital preservation efforts become possible?
Or maybe entirely new applications we can't even really imagine yet, just because storage capacity hasn't been that abundant and cheap before.
What happens when storing almost everything we generate becomes like the default setting? Because it's just so cheap and easy to do.
Yeah, what kind of world do we build when the cost and physical space needed for vast data storage stop being such major constraints? That is definitely something to ponder.
Definitely is.
TechDaily.ai, your source for technical information. This podcast is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup, disaster recovery, hyperconversion in VMware, Hyper-V, Proxmox cluster, AI servers, SA365 turnkey security appliances, and public and private cloud. Check out stonefly.com or email your project requirements to sales@stonefly.com.